Hi, today we're gonna have a look at sequences and series. This is not the one you used to, although we'll start with the basic introduction. We're going to go into the properties, we're going to go into Taylor's and Maclaurin's, and finally we're going to go into the Fourier series. Okay, but before all of this, I first want to talk about what a sequence actually is. So sequence is just a pattern of any numbers, emphasis on the word pattern. So for example, let's say I have the set of numbers 1 2 3 4 5 going all the way until infinity, a very large positive number. Okay, the difference between every single term is 1, so just adding 1 between every single term. So let's say we want to find a general term for the sequence, something you should already know. We have to use the formula an is equal to a1 plus n minus 1d. The first term is 1, and n is for the general term for us to substitute later, n minus 1, leave it as that, and then the difference between every single term is 1, so that gives us the answer of n. So an is n. So if we want to find the 10th term, then a10 is 10, and that would obviously be the case. Okay, but we're gonna go far deeper. Okay, so there are a few things we want to talk about. First of all, we're gonna talk about bounded and unbounded. So the general definition of bounded is that there's some sort of boundary for it. So the sequence sort of stops at some point. So for example, we have a sequence 1 over n. Okay, starting from n equals obviously 1 all the way to infinity. So as we keep substituting numbers inside 1 over n, so for example it would be 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. So see, it keeps getting smaller and smaller. It keeps getting smaller and smaller until we eventually reach 0, because we're counting down smaller and smaller fractions. So I would estimate the bound of this to be somehow 0. It's gonna stop somehow. Or for example, let's say we have minus 1 to the power of n. So as we substitute 1 2 3 4, first if it's an odd number then it's negative, if it's an even number it's positive, odd number negative again. So I mean, it is within the bounds of, so the interval of this is basically minus 1 to 1. So there is some sort of bound for this sequence. Now let's look at unbounded sequences. These are pretty much all sequences that are not bounded by a certain value. For example, let's say we have n square, a simple unbounded sequence. So we have 1, we substitute 2, we get 4, we get 9, we keep substituting, n equals 1 2 3 4 16 and 25, and we go on and on. So the value keeps getting bigger and bigger, approaching positive infinity. So we don't see any known bound inside. There's no boundary at which that this sequence will stop. So as these values keep going up and up, they're obviously unbounded. So that's the first thing I wanted to talk about. Next thing I want to talk about is convergence and divergence. Okay, so we have any sequence an. This is a general term of a sequence. Okay, this sequence is convergent if the limit of an is some value of L. Okay, so we just have to prove this. So the limit as n approaches infinity of an is any value of L. Converging is sort of like bounding. So let's say we have a bunch of values. They're counting down sort of towards one point. They are perhaps not necessarily getting smaller, but they're approaching one point. Whereas diverging is that they're moving away from one point. They keep getting bigger and bigger without any known bound in sight. So to prove that the sequence is in fact converging, we have to find the limit of it. It's as simple as that. So I'm going to give you an example to prove that a particular sequence is actually convergent. So let's say I have the limit as n approaches infinity. Let me just define an. An is n plus minus 1 to the power of n over n. It's a simple n term, so I'm going to substitute this inside this limit to find the limit of this. As n plus minus 1 to the power of n over n. So we just have to do some basic limits now. You should already know this. So I'm going to simplify this first. 1 plus minus 1 to the power of n over n. Okay, from looking at this already, we know that any number over a very large positive number will obviously be 0. So the limit of this sequence is pretty much just limit n approaches infinity 1 plus 0. So the limit is 1. So referring back to the initial requirement for this sequence to converge is that a limit has to exist and it has to equal to some value. So since the limit exists, sequence an is in fact convergent. Okay. Now let's look at a case where it won't necessarily be convergent. Okay, so let's say we have this sequence here. We have an is equal to minus 1 to the power of n multiplied by 1 minus 1 over n. So we're going to find the limit of this sequence. Okay, so I'm going to try to find the limit of this. Okay, so the first thing we have to understand is that there is a minus 1 to the power of n here, and when it comes to this specific format, as we substitute values n equals 1, 2, 3, it keeps interchanging between minus 1 and 1 as n becomes odd and even. So as the sequence moves like this, there is no limit in sight. Okay, so we have to understand. So when n is actually an even number, when n is an even number, then this will equal to 1, and 1 times 1 minus 1 over n is actually just 1 minus 1 over n. But when n is an odd number, then this will become minus 1, because minus 1 to the power of 3 is minus 1. So minus 1 times this term right here is minus 1 plus 1 over n. So this when n is odd, when n is even, and this when n is odd. So for piecewise conditional functions like this, it is already quite obvious that the limit does not exist. So when the limit does not exist, since the limit does not exist, since it does not approach a particular number, it's only switching between two values, we can say that this this sequence is divergent.